So imagine you hire this brilliant assistant to organize a massive, highly sensitive database for your company, right? And their brilliant solution to a storage limit is to just delete half the records so everything fits neatly onto the remaining hard drives.
Oh, wow. Yeah.
Right. Like you get the illusion of this perfectly organized, highly functioning system on the surface. But the underlying data, the actual thing you hired them to protect, is secretly gone.
Right. And you probably don't even find out until you actually need to retrieve a specific file.
Exactly.
Oh.
And by then, the damage is, completely irreversible.
It's a terrifying scenario, honestly. But it really highlights the danger of optimizing for the wrong metric. I mean, when a system prioritizes the appearance of a clean solution over the actual integrity of the work, you end up with, well, localized success, but systemic failure.
Yeah, a solution that just actively sabotages the architecture. Well, welcome to the deep dive. Today, we are looking at that exact phenomenon, but we're looking at it inside the world of automated programming. Our mission for this discussion is to explore the double-edged sword of using AI coding assistants.
Which is something I know a lot of you out there are dealing with daily.
Oh, absolutely. We are going to examine what happens when an AI's seemingly helpful, industry-standard best practice suggestion actually cascades into a hidden mess, a mess that actively undermines your code base.
It's a fascinating topic.
It really is. So we're looking at a breakdown today from a developer named Ang. If you track Haskell development, you might already be familiar with Ang's ongoing blog series where they document various projects and, the challenges they run into.
Right, the Notes on Haskell Programming series.
Yeah, exactly. And we're focusing on a specific entry. This is part 160, written on June 12, 2026, where Ang essentially runs into a brick wall with AI refactoring. The post is specifically exploring the fragility of automated Haskell refactoring, and I gotta say, it is a perfect microcosm of this larger industry issue.
It really is.
Yeah.
And I think what makes Ang's documentation so valuable here is that it captures a very modern, very specific type of friction. Large language models, by their current design, are, they're incredibly adept at generating syntax.
Right, they can write code that looks great.
Exactly. They can produce code that looks elegant, it follows formatting rules, it mimics high-level design patterns perfectly, but they fundamentally lack true semantic understanding.
They don't actually know what they're building.
Right. The model does not understand the broader why behind the code or the holistic architecture of a project. So an AI can suggest a localized change that looks like a massive improvement in isolation.
Like deleting the files to save space.
Yes. But without that holistic understanding, that single suggestion can introduce logical bypasses that basically fundamentally break the underlying constraints of the system.
And whether you are, a seasoned software engineer managing enterprise infrastructure, or maybe you're someone just starting to integrate these AI tools into your daily workflow, this case study from Ang illustrates a pitfall that is completely language agnostic.
Even though we are looking at Haskell today.
Right, exactly. The lessons apply everywhere. So to understand how this trap gets sprung, we kind of have to look at what Ang was actually trying to build when the AI stepped in with its advice.
Okay, let's set the stage.
So Ang is working on a Haskell project that acts as a document processing pipeline. It deals with opening ebooks, running Pandoc, which if you don't know is this incredibly powerful, widely used document converter, and then generating PDFs using a typesetting system called TIPST.
And, complex document conversion pipelines are notoriously error-prone.
Oh, yeah.
Simply because you are relying on so many external systems and file formats, it's messy.
Yeah.
And in the original version of Ang's code, when an error occurred somewhere in this pipeline, the underlying details of that failure were being flattened into generic string types.
Just raw text.
Basically, yeah. The custom appr type that Ang built was essentially just catching the failure and spitting out basic text.
Which is kind of like the check engine light on your dashboard, right?
That is a perfect analogy.
Like it tells you something is wrong, but literally nothing else. It crashed, but you can't easily parse a generic string to figure out the recovery path.
Right, versus having a diagnostic scanner that tells you exactly which sensor failed.
Exactly. So the AI analyzes this custom appr type, and it suggests upgrading to structured error data. It essentially tells Ang to, stop throwing away the error context and start preserving the specific type-safe data of the failure.
And we should clarify, from a purely theoretical software engineering standpoint, the AI is giving excellent advice here.
It sounds like a massive improvement on paper. I mean, why wouldn't we want this?
Well, because preserving structured error data is an industry standard for a reason.
Hmm.
It allows a program to handle different failures in highly customized programmatic ways.
Right.
So if you look at the architecture of Ang's project, the system might encounter a file not found error, or it might encounter an invalid E to F8 error, meaning the text encoding is corrupted.
Two completely different problems.
Exactly. Or perhaps a template error generated while compiling a Panda template. Now, if all of those distinct failures are just flattened into raw text strings, the program cannot easily differentiate between them at runtime to decide how to recover.
It's just going to panic and shut down.
Most likely, it'll just halt execution. But with structured, distinct data types, the program's logic can route the failure. It can detect a file not found error and trigger a prompt for the user to select a different directory.
Oh, I see.
Yeah, whereas an invalid F8 error might trigger an automatic fallback to a different text encoding. It gives the system programmatic control over its own recovery process.
So Aang receives this suggestion and obviously agrees. I mean, it makes total sense to upgrade to a structured format. So Aang starts updating the type signature of the apprer to wrap these specific underlying types.
Which is where things start to get tricky.
Right. According to the source material, this involved pulling in types like IO exception. So that's to handle things like an open failed error when an output file refuses to open.
Right.
And also pulling in pandoChar to catch runtime errors during the actual document conversion process. So the goal is to build this highly detailed, deeply nested error type.
But this introduces a massive collision with the environment they're working in.
Yes, because Haskell is not a language that allows you to play fast and loose with data structures.
No, it is not. Haskell enforces an incredibly strict, mathematically rigorous type system. And this AI suggestion introduces a fatal complication regarding how Haskell evaluates equality.
Which sounds incredibly nerdy, but it breaks the whole thing.
It really does. By introducing IO exception and pandoChar into the structure of apprer, the code suddenly violates the constraints of a core Haskell feature known as the EQ type class.
Right. The source notes that because these specific external types are now embedded inside the custom error structure, and could no longer use a very standard, very simple Haskell command. And that command is deriving, open parenthesis, eq, comma, show, close parenthesis.
Deriving EQ show,
Yeah.
a staple of Haskell development.
Yeah, if you've worked with Haskell, you know how convenient that deriving clause is. But for the sake of clarity for everyone listening, why would adding an input-output exception to a data structure cause the compiler to just completely reject a basic equality check?
Well, it requires looking at what that deriving keyword actually does under the hood. So in Haskell, EQ is the type class responsible for testing equality.
Like, is A equal to B?
Exactly. And show is the type class for converting data into a readable string format so you can print it out. When a developer writes deriving EQ show at the end of a data declaration, they're invoking a really powerful compiler feature.
It's like a shortcut, right?
It is a massive shortcut. They're instructing the Haskell compiler to automatically generate the boilerplate syntax required to compare two instances of this data structure and to print it.
So the human doesn't have to write it all out.
Right. The compiler analyzes the structure, looks at every single property inside of it, and auto-generates the logic that says if property A matches property A and property B matches property B, then these two complex objects are mathematically equal.
That's an incredible time saver. You don't have to manually write out the comparison logic for every single field in your data structure. The compiler just handles the tedious verification.
It does, but there's a catch. The compiler can only auto-generate that logic if every single piece of data embedded inside that structure already has its own established rules for equality.
And that is the breaking point.
That is exactly the breaking point. The AI instructed Aang to embed IO exception into the structured error. But an IO exception in Haskell does not implement the EQ type class.
It doesn't know how to compare them.
No, it does not have predefined rules for equality. And if you think about what an IO exception actually represents conceptually, it becomes pretty clear why it lacks those rules.
Why is that?
Well, an input-output exception is deeply tied to the physical state of the operating system at a highly specific moment in time.
Oh, I see where this is going.
Yeah, so if your program fails to open a file at 2:00 p.m., this is a network drive timeout, right? And then it fails to open a file at 2:01 p.m. because a different user locked the read permissions.
Yeah.
How do you definitively mathematically prove those two errors are structurally identical?
You can't. I mean, they involve external state, timestamps, OS level permission flags.
Exactly. They're inherently messy real-world events. And Haskell is a pure functional language. It demands absolute predictability.
So when the Haskell compiler reaches this new AppError type, it sees the command to automatically derive equality. It starts analyzing the structure, it hits that IO exception buried inside, realizes there is absolutely no mathematically sound way to compare two operating system exceptions, and it just completely halts.
The compiler refuses to guess. It enforces safety by demanding explicit instructions. If it cannot guarantee the absolute accuracy of an equality check, it simply will not compile the code.
Wow.
So the AI's attempt to force an industry best practice, structured error data onto a system without understanding the strict type class constraints of the underlying language, it resulted in a fundamentally broken architecture. The project is just dead in the water.
Which is a classic development bottleneck, isn't it? You attempt a refactor, you hit a compiler wall, and you have to find a workaround.
Happens all the time.
So because the simple automated deriving EQ show command has been rejected by the strict compiler, the AI coding assistant steps back in to offer a solution to the very problem it just created.
And this is where things go from bad to worse.
Oh, yeah. This is where the dynamic shifts from a simple compiler error to a massive logical vulnerability. The AI generates what Ang specifically identifies as a code smell.
And we should define that, because the concept of a code smell is really crucial here. In software engineering, a code smell is not necessarily a syntax error that crashes the program.
Right, the code might actually run.
Exactly. It might technically compile and execute, but it's a surface-level indicator that usually points to a deeper, more systemic flaw in the system's design. It's code that is clumsy, it violates core design principles, or it requires, excessive mental gymnastics to justify.
It's like when you see duct tape on an airplane wing. Like, technically it's holding, but something structurally is wrong.
That's a great way to put it. It indicates that the architecture is straining under its own weight.
And the workaround the AI provides here is the textbook definition of straining the architecture. According to Ang's notes, the only way to move forward was to drop the automatic derivation of equality completely.
They had to abandon the shortcut.
Yeah, they had to switch to deriving stock, show, just to maintain the ability to print the errors. And then they had to manually write out a custom EQ instance.
Which is tedious.
Extremely. They had to write out the mathematical rules for equality by hand for every single error type in the project. And, naturally, the AI generated the boilerplate code for this massive manual fix.
And looking closely at the code provided in the source, we can actually see how the AI handles the simpler error types perfectly fine.
Right. It gets some of them right.
Yeah. For example, it generated this line for file path errors. It wrote, file not found fp1 equals file not found fp2 equals sp1 equals fp2.
Which is entirely logical. It essentially tells the program that if the file path associated with the first error is exactly the same as the file path associated with the second error, then the two file not found errors are identical.
Right, it's checking the internal data.
Yeah, and it generated a similar rule for template errors, like template error S1 equals S1 equals SS2. It is actively inspecting the nested information there.
But then the AI has to generate the manual equality rules for the problematic errors. The external types that caused the compiler to halt in the first place, the panda cruntum error and the open failed error.
The messy real-world ones?
Exactly. And the AI cannot rely on a simple data comparison here, because as we established earlier, there are no established rules for comparing those complex underlying types.
And the code the AI generates to solve this is just staggering. For the pandic errors, it writes, panda cruntum error is cruntum error true.
Unbelievable.
And then for the IO errors, it writes, open failed, true. And then it adds a final catch-all clause at the very bottom of the block. False.
And this right here is the exact code smell Ang identified.
Yeah, let's unpack that.
The critical element in these lines of code is the underscore symbol. In Haskell, the underscore is a wildcard character used in pattern matching.
Okay.
When a developer, or in this case an AI, places an underscore in a variable position, it's explicitly telling the Haskell compiler, I acknowledge that there is a piece of data nested here, but I do not care what it is, I'm not going to inspect it, and I want you to intentionally discard it during this operation.
Wow. It is literally a deliberate blindfold.
It really is.
By writing panda cruntum error equals panda cruntum error x true, the AI is creating a rule that says, if the first error you encounter is a pandic error, and the second error is also a pandic error, automatically declare them equal and return true.
Yep.
Completely ignore all of the complex runtime data, the timestamps, the specific failure codes. Ignore everything inside the structure. Just look at the outer wrapper.
The system is now treating a critical failure, like, say, rendering a complex graph exactly the same as a minor warning about a missing font file, simply because they both happen to be wrapped in a panda quantum error label.
That is insane.
The AI is forcing the equality check to return true purely by bypassing the very data it was supposed to evaluate.
The irony here is almost painful. I mean, let's trace the logic of this entire interaction.
Let's do it.
The AI coding assistant initiated this massive refactoring process specifically to upgrade the system from generic strings to structured data, arguing that preserving the underlying error details was a critical best practice.
Right, the diagnostic scanner upgrade.
Right. It forced the developer to rewrite the entire error handling architecture to capture those details. Then, when that new architecture caused a compiler failure, the AI solved the failure by using wildcard characters to permanently discard the exact details it just forced the developer to preserve.
It's completely self-defeating. The AI optimized for the immediate constraint without understanding the overarching semantic goal.
It just wanted to make the red text go away.
Exactly. The AI was given a highly localized prompt. The code will not compile because these specific error types lack an EQ instance. So the AI found the path of absolute least resistance to silence the compiler.
Which was the wildcard.
Yeah, it recognized that using a wildcard character would bypass the strict data comparison, effectively muting the compiler's safety check. It never evaluated the semantic purpose of the data. It achieved the immediate goal, which was compilation, by basically sacrificing the structural integrity of the entire error handling system.
Okay, but wait, I have to challenge this framing a little bit. If we are looking at the realities of software development, isn't it entirely the developer's responsibility to review the code being committed to the project? I mean, Aang openly admits in the source post that they actually missed this specific code smell earlier in the process.
That's true.
It slipped right past them during the review. So why are we blaming the AI's generation when the human developer is the one who literally hit approve without adequately reviewing the logical implications of those wildcards?
It is a totally valid challenge, and you're right, accountability does ultimately reside with the human engineer. The code does not enter production without human approval.
Right.
But what makes this uniquely dangerous, and honestly why Aang's documentation is so vital, is the psychological trap the AI sets during the review process.
The psychological trap.
Yeah, when an AI generates a large block of manual boilerplate code like this massive custom EQ instance, it rarely generates entirely garbage code. It generates code where 90% of logic is perfectly sound, structurally accurate, and highly readable.
Oh, right, because the found not found comparison it wrote earlier was completely accurate.
Exactly. It demonstrated that the AI knew exactly how to compare nested variables.
Okay, I see what you mean.
And that creates cognitive fatigue. When a developer reviews the first 3 or 4 lines of a generated block, and those lines demonstrate a perfect grasp of the required logic, the human brain naturally assumes the remaining lines follow the exact same logical pattern.
You just skim the rest.
You skim it. You see the compiler light turn green, you verify the program executes, and you just move on to the next problem. The trap is sprung not because the AI overpowered the developer, but because it lulled the developer into a false sense of security through partial accuracy.
That is so true. A compiler error is loud and obvious. But a wildcard true return is a silent, logical bug.
It's invisible.
It could exist in a codebase for years, silently corrupting the error recovery state before anyone even realizes the data is being thrown away.
Precisely.
Man, that makes the situation infinitely more complex for the human sitting at the keyboard. Based on the source material, Aang concludes that developers navigating this landscape are basically left with 2 primary options.
Yeah, and neither is perfect.
No. So the first takeaway Aang presents is that developers might have to start subscribing to frontier AI models. Aang notes they were using a freely available model during this project and hypothesizes that the massive, expensive cutting-edge models might actually possess enough contextual awareness to avoid suggesting a wildcard bypass for data it just recommended preserving.
It's a hypothesis. And Aang's alternative takeaway is equally demanding, honestly.
What's that?
If a developer cannot or will not rely on frontier models, they must adopt an aggressive posture of steering the model. They just cannot accept the first generated block of code.
They have to micromanage it.
Exactly. They have to actively manage the machine, forcefully prompting it to suggest the simplest, most direct solutions, and constantly verifying that the AI hasn't taken a lazy, destructive shortcut to appease the compiler.
And we aren't here to say whether paying for a frontier model is the definitive answer for the industry, but it is clearly the perspective Ang arrived at after navigating this localized disaster.
Yeah.
It fundamentally shifts the role of the software engineer. You're no longer just writing syntax from scratch. You are acting as an auditor, a rigorous editor, and a manager to an assistant that is highly capable but dangerously literal.
Dangerously literal is a great phrase for it.
If Ang did not possess a deep foundational understanding of how Haskell type classes function, or what the underscore wildcard actually commands the compiler to do, that code smell would have become a permanent, silent flaw in the architecture.
But according to the Post, Ang takes away a remarkably positive perspective from the whole ordeal.
Really, after all of that.
Yeah, surprisingly. Ang concludes that the core value of the experience wasn't actually in getting the code to compile, but in the friction itself.
The learning process.
Right. The entire purpose of the Notes on Haskell Programming series is that ongoing process of learning. Hitting that wall, analyzing the AI's flawed workaround, and really deconstructing the failure provided a much deeper understanding of both Haskell's internal mechanics and the behavioral quirks of large language models.
It forces a developer to articulate their own design intentions with absolute clarity.
Because the AI will not infer them.
Exactly. So we started with a seemingly brilliant AI suggestion to upgrade a Haskell project's error handling to use industry-standard structured data.
Good intention.
Right. But that suggestion, while technically sound in theory, collided violently with Haskell's strict type system because complex external errors, like operating system exceptions, just do not naturally possess the mathematical instructions required for a quality comparison.
They're too messy.
Yep. So to bypass the resulting compiler block, the AI generated a custom workaround utilizing wildcards. And this lazy fix effectively blinded the system, permanently ignoring the highly specific error data it was explicitly designed to preserve, all just to force the program to compile.
It is a profound example of an automated tool treating the symptom while actively exacerbating the disease.
Perfectly said.
It really serves as a necessary cautionary tale regarding the illusion of seamless automation in complex systems. And as these AI coding assistants become more deeply embedded in enterprise workflows and our daily development cycles, I think it leaves us grappling with a critical, almost philosophical problem regarding the economics of our own attention.
The economics of attention. That is a fascinating angle. What is the final takeaway here regarding our attention?
Well, think about it. If human developers have to remain hypervigilant at all times, exhaustively reviewing every single line of AI-generated boilerplate to catch these incredibly subtle, silent, logical bypasses.
Like an AI secretly declaring all complex errors mathematically equal just to make a red compiler warning disappear.
Exactly. If we have to do that constantly, we have to seriously question the return on investment. Does the sheer exhausting cognitive load of deeply auditing and verifying an AI's hallucinated code eventually surpass the time, effort, and mental energy it would have taken to simply architect and write the correct code ourselves in the first place?
Are we actually accelerating our workflow, or are we just shifting our mental effort from the creative act of building a system to the paranoid act of interrogating an assistant who might be secretly throwing our data into a void?
That's the real question you have to ask.
That is an incredible thought to leave on. Thank you for joining us on this deep dive into the realities of automated programming. Keep analyzing your systems, keep questioning the tools you integrate into your workflow, and, never implicitly trust a wildcard that you didn't write yourself.